Thank you everyone again. This is module number 3. As we already went through a number of visualization features in NeXTA, so I would like to just have a quick list of the basic GUI elements again. Through this presentation form, I want to make sure you can go through those GUI interface one more time to make sure you are not encountering any major issues in understanding the NeXTA interface. And then followed by this introduction, I would like to show you how to import the typical demand file from a planning package or from the planning organization database. And then I will describe very quickly what are the major issues when you try to calibrate the traffic flow capacity, traffic flow density parameters when you deploy for a real-life application. So I will go through the GUI interface to help you to understand how to edit and view the NeXTA project menu in the integration with the traffic assignment, advanced visualization, and the link MOE display. So as we talk about here again, the basic GIS layer, and when you do a project selection, you can try to have the project specific information. Again, all the project files are stored in the CSV file except for two major files. One is a binary file for agent trajectory. The other is a link MOE file for a link MOE trajectory. But those two files also have the corresponding CSV file for you to view it, to understand it. Okay. So here is all the major input and output files. So for something began with ODME, those are the advanced feature for OD demand calibration. And the option files specify all the vehicle type you might need for emission. The optional file MOE setting, you can specify a customized MOE statistic calculation. Okay. The output file here including day-by-day MOE, output link MOE, and output link TD MOE. The TD stands for specify as a time-dependent MOE files. So typically, I would like to ask you to go through this project file, to go through this network data, demand database, traffic management scenario database. Basically, is a scenario with a work zone, link capacity, and also some scenario-based information. Then number 4 step is perform the traffic simulation and then see the traffic assignment results. Okay. In the traffic simulation or the traffic assignment, you have a selection of point queue model at the current step and the newest kinematic wave model. And then for the traffic representation to be detailed in the next slides on the next session, we are talking about different level of traffic representation. And then you can also specify the number of days for your traffic assignment package. If you specify, as in this case, just one iteration, then this means all the vehicles are using the shortest path. Okay, so we have this time clock bar, this 24-hour time clock bar to visualize the traffic MOE at a different stage. We have volume, density, speed, and then you can do the animation for the queue and for the different bandwidth. Okay. So we also simulate the agent by agent. Each agent again represents the one vehicle or represents one traveler agent. And then to do so, we automatically turn off the node layer and to show the bandwidth. On this link button, we show a sorted list of the link attributes. You can specify different V over C, total link volume, total delay to sort this link performance throughout the network. And you can also open up this link or path MOE layer. So we can display the link MOE, path MOE, and then we can use this vehicle statistic chart to specify all the detailed information. So if you go to the lesson 2, we use this GNU plot to plot this time and the space diagram based on the simulation results. So on this vehicle layer, on this vehicle summary dialog, we can really show you a layered hierarchical structure of information from O, D, to different demand type, to different vehicle type, to different path, and then to different vehicles along this way. For the user who is interested in understanding the user equilibrium, they can go to this path list to see how the different path being selected, but always make sure, you need to make sure this departure time being selected. One user, they just specify for a 24 hour, then they look at the different path, then they say, your user equilibrium has not been reached because the different path has a different travel time. I have to respond that you have to really just be a little bit careful. You need to look at the specific departure time. At a specific departure time interval, then different path will have the similar travel time. But if you compare the path travel time across a longer time period, and then they may have different travel time depending on the traffic congestion. Okay, the last button here is a summary. As I illustrate here, you can try to have different departure time interval, different number of vehicles, and then for doing so, you can have different display. Okay, along the way. So in the tool, we are adding a number of processing tools for you to export the data into the 3-dimensional KML file, which can be visualized the 3D animation in the Google Earth. You need to install the Google Earth for sure. And then we can also have the zone level display to adjust the height and the color if you follow the suggestion. So in this module 4, I would like to go to this workshop exercise. So since we already go through some detailed steps already, so I would like to spend just about 10 minutes to go through these data preparation steps for building a regional level traffic network, and then tell you to share some experience about how to calibrate a real life network. So here is a long list of the data files you need to specify, but we start with the GIS shapefile. So typically in the planning organization, they have these GIS shapefile available, such as node shapefile, link shapefile, and zone shapefile. Then we use item number 2, input the GIS setting to specify the link information. So let me try to just switch to the network. So in our package, if you go to the data set number 4, GIS import. Okay. So we have this GIS importing tool as the NeXTA interface. Okay. And then we have some GIS sampling file with the import GIS setting file with the import shape file as we specify from here. Okay. All those shape files can be visualized using ArcGIS or OpenGIS QGIS package. So with all the data available here, we click on this NeXTA GIS importing tool. So this NeXTA GIS importing tool is a 32-bit version. Okay. This version has a clean interface because this tool is only used for the data importing activity. Go to the file, import the QGIS or the GIS package. Next, we can try to just go to this particular folder. So this is a cube sample GIS setup. I have this importing GIS setting file. Open. And going through this detailed information, input node, input link. Okay. And then I can simply just click on this importing button. click on OK, then you import the shape file into this setup. After doing so, you can save the network as is, and then all the data will be stored in the current folder. So let me try one more time with you guys. So here is the cube shape file. Okay. So before doing so, I only just use a clean version of import file. Okay. So what I have here is import JS setting, import link type. The import JS setting, if you click on this file, we have a detailed guideline information users guide. This is the 3 files. The value here specifies the file name. And for the node layer, this aim is the corresponding field name for node type. TAZ ID is a corresponding TAZ field name for the TAZ. So this column here is the DTA light representation. This column here is the shapefile representation. Okay. So again, we only need 2 files. One is import JS setting. The other is the input link type. The input link type specified if you have different link type. For example, this is the link type code, and then we know how I can convert this link type. By using this link type information, how I can generate the default capacity speed limit for the DTA light setup. So let me try to show this process one more time with you. So before I'm doing so, this folder is clean except for these 2 files. Okay. Then I do the file. I new the file project. Import the JS setting. Okay. I can do the import JS as long as it has a import link type and the JS setting. Import it. Okay, and we use some default setup. So all the data will be stored. So after I just look at my operation, if you do save, replace this folder, save, you can see instantly all those files will be automatically produced. And then you can check further, input link, input node, and so the NeXTA is a tool for us to export the DTA standard output and import the GIS file very easily. Okay, because a different software package such as Transcat or vSoom, they have different conventions. So we just put some sample GS file for you to look at. Okay. So now after you prepared 1A, 1B, 1C, you get this import JS setting. Yeah, these are 3A, 3B, 3C, 3D as an additional, optional definitional file. You prepare your demand file at item number 4, and then you prepare your import file list, import scenario setting, and then we can do the traffic simulation quickly. For the planners who wants to do the traffic demand calibration, they need to also prepare the scenario count, scenario sensor, and the scenario work zone, and all the other information can be easily prepared. Okay, so I'll go through this step-by-step process one more time. 1A, 1B, 1C are the node shape file, link shape file, zone shape file. So for the users, you might need to know that the essential file is a link shape file. In some cases, you only have the one link shape file without the node and without the zone. The DTA light or the NeXTA importing utility still allow you to import the single link layer and then automatically generate the nodes based on the form node and the to node, and then make them connected. So you need to check out this option with only one link shapefile. Okay. In this import JS setting file, we have this a little bit detailed configuration. You have any issues, first of all, you can go to the document number 3, learning document for the JS importing, and then you can also ask some advanced users for the help. As long as you get through this hurdle, you can import the JS setup very easily from many available JS package. Okay. For this link type file, we use them to generate the default link capacity, speed limit, gem density. So step number 4 here is run this executable, and then we select the import JS setting. Then as a one example, we got the one MPO's dataset. We can convert the dataset very easily. Here is Atlanta network. Okay, and then for the demand file, I strongly encourage the users to look at the demand file list, prepare this one manually, and we do allow a full list of the different demand format, such as column format, matrix format, full matrix format, dense format, agent file, and then since this is open source package, you can further extend this importing file by yourself. Okay, and as an example here, in this demand file list, and we have more than 20 or even 30 different files, and then each file you can try to use the original file name, the format type, and you can then specify the starting time, ending time in seconds or in minutes, and then the corresponding demand type, so that you can do a more advanced demand management application. Okay, to select the sensor count, to prepare the sensor count, sensor, we have another session to teach you how to utilize and prepare the corresponding information. We'll defer that to the next few sessions. For the work zone evaluation is related to any capacity reduction application. So you need to specify the day or the time period defined by starting day, ending day, and the capacity reduction percentage for the link layer, and the corresponding speed limit and the work zone condition. VMS, you can also specify the scenario VMS time. The tolling application, as we described before, you can specify the starting time, ending time, and the toll charge. Okay, for the emission evaluation, you can prepare the vehicle emission rate as a part of the MOE slide, which is the collaboration result between my research team and the interstate research team led by Nagi Raphael and Chris Free. Import scenario setting. To be familiar with this import scenario setting, you need to understand the number of iterations, essentially is the number of days, different traffic flow model, different signal representation, and then how to select the different random number seeds. Once you go through these few parameters, get yourself familiar with this input scenario setting, then you can go on to perform a more advanced OD demand estimation. So in the next 5 minutes, I would like to go through a very quick calibration process to teach you how you can convert from a regional static traffic flow model to a mesoscopic traffic flow model, and then what you need to understand, what are the potential pitfalls of this data conversion. So this presentation is prepared by my former team member, Jeff Taylor. He is a very dedicated student. After we import the Clackamas network, Clackamas is a small county in the Portland region in the United States. After the first simulation run, everything is gridlock. So if you look at the static traffic assignment, they have VOC, the BPR function. So they do not have the specific capacity constraint. So they always allow the vehicle being flow into the network and run out of the network. the major difference between the DTA and the static traffic assignment is that if the DTA impose a very restricted capacity constraint. For the point queue, we impose the capacity constraint at the downstream. From the spatial queue, we impose the capacity constraint also throughout the storage, using the storage capacity. For the kinematic wave, we impose this queue spillback all the way through the backward wave propagation line. So more advanced traffic flow model you have, more constraints you add. So essentially, the DTA is a capacitated traffic assignment. So by understanding this, then you can try to see how the Jeff Taylor, when he finished his first simulation run, everything becomes a gray log. The reason is that we add in too many capacity constraints. So we look at the freeway segment, almost no traffic or very limited traffic, or traffic is a free flow, and on the arterial street, here is a gray log. So we say, okay, in this case, it's more likely the ramp offload capacity is not enough. So we increase the ramp offload capacity. Original ramp offload capacity is 1,400 vehicles per hour per lane. We increase offload capacity. Still, we have significant gray log. Then we look at, do we have any storage capacity issue? Do we have any inflow capacity ratio issue? So then we look at the detailed geometry details. So look at this particular ramp. The offload ramp has one lane. The inflow section has two lanes. So essentially, you have two lanes in, one lane out. So essentially, your storage capacity should be coded very carefully. This could be 300 or even 400 vehicles per mile per lane, okay, or per lap per facility. But unfortunately, in the planning model, typically they code this as a one lane, even it's a two lane ramp, and then even you have a reasonable offload flow capacity, you have not considered this storage capacity well, and then we are creating these potential issues. So that's why we need to be extremely careful when you try to convert from a planning package to a dynamic traffic assignment package. So since we do not know exactly what are the jam density in this region, so I was working with Jeff Taylor to do a sensitivity analysis. Here is the jam density. We change the jam density for the whole network from, if you look at this travel time index, which is the mean travel time divided by free flow travel time. Okay, this travel time index from 10 all the way decreased to a reasonable value. The average speed becomes a much more reasonable. So by changing this jam density, by changing this storage capacity, we are reaching the degree that we can have a reasonable representation for this traffic flow dynamics. So the third attempt we do, we reset the offload capacity, we adjust the inflow and the storage capacity, and then have a number of combination of modifications. We are reaching a much more reasonable traffic simulation. By the end of the day, here is a recommendation. The macroscopic capacity might not be the appropriate for the mesoscopic capacity constraint. You have to understand the traffic flow model just as we described today about the inflow capacity, outflow capacity, the queue propagation. You understand this traffic flow model so you can understand the limitation and to handle the special case, such as we have two lane facility being coded as a one lane on ramp or off ramp. Then you need to simultaneously adjust the capacity before OD demand estimation. Don't try to just import the data, run the simulation. You need to carefully explore this capacity issue. And also always start with a fewer capacity constraint, such as a point queue, and then you can try spatial queue. Then you can try to have the shock wave propagation so that you can add in a fewer capacity constraint to make sure you can have a realistic setup without having these potentially unrealistic bottlenecks. So this is the first major session of our full module introduction. If you have further questions, you can send the comments to my team, to me in this email. And since this is an open source package, you are more than welcome to contribute your knowledge, your testing cases, and also your source code into our community. Thank you.